Hello there. So my name is Aditya and I'm part of Team BIOS and I play as a reverse engineer in that team. So today in this video I'll be walking you through a basic reversing challenge and explaining the methodology and the thought process of how to solve a particular challenge. So let's get started. Before starting, I'll actually recommend you to learn assembly as well as C programming language. Just the basics, not really in depth, but as a prerequisite, knowing both of these languages will really help in solving a reversing challenge, and I'll show you why. As well as it's really good if you actually install Linux. You can install Linux through any ways. Multiple ways are there. You can install it as into WSL, or you can install it using VMs, or you can even dual boot it. You can search those up in Google, so it should be fine. So let's try downloading a challenge from the site. So I'm right now in Traboda.com, and they do offer plenty of challenges. So let's choose a reversing challenge out of this. Let's look for easy challenge. Let's see. Maybe I can choose replicants. Okay. So let's try downloading this challenge. So I have it already downloaded. You can just press on download attachment and press on this particular link, and it should download automatically. I have it already downloaded, so I'm not going to re-download it again. Answer the binary correctly, and you get a flag. All right. Let's look into what the binary has to offer. Uh, so what is reverse engineering? So reverse engineering is basically an art of actually understanding what the program does, and in specific to CTFs, you will need to understand what kind of an input you're supposed to supply so that you get a particular output that you design. So that's what reverse engineering is basically in CTFs. So you try to analyze the binary and you see what kind of an input you're supposed to give in order to get the output that you actually want. How do you do that? There are two methodologies involved in reverse engineering. One is called static analysis and one is called dynamic analysis. In static analysis, you basically use a particular set of tools and you put the use the tools to analyze the particular challenge file that you got, and you might you will not run the program, rather you will just look into that particular challenge file. So you'll just dissect it and you will understand what it is doing without running the program. I'll show you how to do that, and that's what static analysis is meant. Dynamic analysis is where you actually run the program. You try to understand how it behaves and how it actually gives you what kind of different outputs it's giving you when you're giving different kinds of an input and stuff. That's what dynamic analysis does. In static analysis, there are plenty of tools available. A few of those are IDAPro, Ghidra, Binary Ninja, and stuff. Out of this, Ghidra is actually free and open source. So you can download Ghidra from GitHub. You can just Google that out, and you can install it, and you can solve it using that. For dynamic analysis, the most popular one you can use is GDB. So another name for dynamic analysis is actually like debugging the program. So you actually run through the program one line by line. So like what a program is, right? So you run through the program line by line, seeing how it changes. So through every line, how the particular program changes, and depending on those, you actually theorize what kind of an input you can actually give to that particular program. So that is what dynamic analysis is. So in static analysis, we'll be using Ghidra in this particular video. So once you load up Ghidra, this is how it looks like. You can create a new project over here, press next, give the project name, press finish, and that should create a folder like this. So that's how I created the CT folder. And to just drag and drop this particular file over here, which is our challenge file, and it should get loaded. Before doing this, two things can be done. One is actually running a particular a command to understand what kind of a file you are dealing with. So there are actually many types of file, out of which two are majoritarily involved in reverse engineering. One is called ELF and one is called exe file. I'll show you what it is. So I run a command called file and I run this. Now we see like there are plenty of information here, not to worry. We just need to focus on this two information over here. So ELF 32-bit and now strip. So 32-bit and 64-bit are like two different types of architectures. You can Google what in detail what it is. There isn't much difference in between them, so I will not really go into details. Only the details really matter, and you will actually learn those details once you start solving most of the challenges. The second thing that we are seeing is ELF. So what is ELF? You might have seen like in your Windows PC and stuff, you will see exe, right? So when you're running a program, you double click on it and you actually run it, right? And those programs are basically what you call executables. So in Windows, it's called an exe. It comes under the format called PE32, or generally called as exe. Or and in Linux, it's called as an ELF. So that's the only difference. So a program which runs in different operating systems are called with two different names. One is called an exe and one is called an ELF. Now, the second thing that you need to see is like stripped and not stripped. So those are two different terms. So stripped is basically in which the information. So once you are making a C program and once you compile it, you get an object file, right? So in that object file, you will get a lot of information. Now imagine you want to give it to someone and you don't actually want you want his life to make be really tough while reverse engineering. So if you want to do that, you make it stripped. So you actually turn up some kind of options in while you're compiling, and the output that you get will be having no information at all. Like no, it's called debug info. So you'll not be having any kind of debug information in that. So that's basically what you call like removing the function names, removing the variable names, removing any kind of information that you supplied as a programmer into the program will not be there in the final file that you're getting. So that's what stripped is. Non-stripped is where it's really easy. So in not stripped binaries, you will actually have what kind of a function is there, what all names the function have, what kind of names the variables have. All those stuff are already there. So it's really easy to reverse a not stripped binary than a stripped binary. So in this case, we are dealing with a not strip, which is really good for us, and we'll try analyzing it. So let's double click on this to start analyzing this, please. So as I said, you can try with two different ways. So one I did was file and the challenge name, right? So I'll try doing one more tool called strings. The strings is a simple Linux tool which will actually see what kind of readable sentences, phrases, words, or some terms that is there in that particular challenge file can be extracted. So this extracts all those information out of this. So if you see lot of info, right? Now, most of these are actually general for every challenge. So every challenge file will have like these set of general information. Let's see what actually stands out. Okay, so we can see that these two sentences stand out. So one is why did you save me, and the second is to say something. Is there something else which stands out? I think not. Let's keep those in mind. We are not sure why or what it is used for, but let's keep those in mind. Before going to analysis, let's maybe try running the program once. Why did you save me? I'm not sure. Exited. Okay, so I think we are supposed to supply the right input to it. So let's find out what kind of an input we are actually asked to supply so that we'll get the right output. Most likely the flag. Okay, so this is how Ghidras and the window looks like, and there's a lot of things going on over here, but you don't need to focus on any of those. We need to focus only on three things: this window over here on the left side, the middle window, and the right side. So I'll explain what all those three things are. So in this, there are a lot of things, and right now we don't need to focus on any of those except this particular thing called functions. So if you have already done C programming, you would know that in C program, every program that is that is executed will start running from a particular function called main. No matter how many functions is there, it will always start under a particular function called main. So that's where we also need to start. So since this is most likely to be a C program, we will actually run. When we are actually running, main is the function which actually runs the program, right? So let's try running the program. And when we run the program, we get this particular function. So most likely this is coming from the main function itself. So So inside this, let's look for a function name called main. It should be somewhere around here. There we go. So we see two functions. We'll see into what print flag does. But before that, let's see into what main does. When I click main, things change over at this two window, right? What you see at this window is called a disassembly, and what you see at this window is called a decompiled, function, or decompiled version of the particular disassembly. These two are two different terms. So disassembly is basically in the listing of the assembly language that the program is created. Once the program is compiled, you get the object file, right? So this is the dissected version of that object file, and what you see over here is the assembly language, a machine language, or to speak. So that's why I told you to understand reverse engineering a little bit in depth. You will need to learn a bit of reverse assembly language. So all these instructions are basically what assembly language basically contains. So to learn that, you can either refer BIOS wiki, or you can search for YouTube videos regarding that and stuff. And in the right side, you see a decompiled view of that particular assembly. So decompiled view is basically what the particular tool, in this case Ghidra, does. Like, it starts to guess what the actual source code, what the actual program that the actual creator looked like, and it actually tries to guess that. So using this, we can actually see, okay, so this might be how the actual program looked like. And in most cases, both are in sync. But in some cases, maybe this both can be out of sync, in which case, like, assembly is a better option to look for. So reading assembly is a better option than rather looking at always in the decompiled view. So this might sometimes have some errors because it's always like a guess rather than the accurate form. So that's why. So let's look into what the program has to offer now. We see main, we see multiple variables being initialized. Well, if you know C, and you will instantly understand what all this stuff are happening. So you don't need to care about these two lines over here. These are basically like the standard lines, and also these lines. So what we need to care about is like maybe from here. This is also really not required. Just these lines. So let's see what it is. Okay, so we see that why did you save me is over here. So it's printed. So this main function prints the statement called why did you save me, and we can see that over here. And then what it does is it waits for our input. So scanf is basically the function which waits for our input. And if you know C programming, once again, yeah, you will know that it takes a particular string. So a string is stored into local 64, the variable called local 64, and the size of local 64 is 80 characters. So whatever we are supplying is getting stored into local 64, and then it is getting compared with to say something, the word phrase to say something. So that is what string compare does. It compares two different variables. So one is local 64 and another one is to say something. So most likely from this we can try to understand that if our our comparison returns out to be actually true, that is, if our input is same as the phrase to say something, then we will call print flag, else we'll just exit straight. We can give this input and see, but before that, let's see what actually print flag has to offer. So let's try to double click on this using the function name. Like right now you have the function name, right, called print flag. That's because this is a non-strip binary. So in a strip binary, you won't see this function name called print flag. From this function itself, you can kind of theorize that this function may be responsible for printing the flag in some kind of a form. So you got a little bit of information from the function name itself. In a strip binary, you don't have that information. You actually got to analyze the whole function itself. So okay, this function looks really long, but let's try to take part by part. So in this first, we see that there's plenty of variables initialized, and if we scroll down, we can see many of those hex bytes are initialized, put into those variables. Let's maybe try seeing what those hex bytes are. So let me spin off IPython, IPython is just interactive Python console. So I think most of you have heard of Python, right? So IPython is just the way you can actually interact with Python, easily than rather than maybe writing a program and running it using Python itself. Rather than that, you can just give line by line and see what kind of an input output is happening. So right now we need to see what the hex value 0x6f is. 0x6f. Okay, it's 111 in decimal. What could it be? So one thing that you can maybe come out of experience is that uh, like all the hex values, if it is inside the range of decimal value 32, if it is inside the range of 32 and maybe 127, it is most likely to be a character. Why I say that? Because in the range of ASCII, which you can Google what ASCII is. So like every character, that every letter that you're actually typing into the program is not actually stored as that letter itself. So inside the memory, inside that particular program memory, that particular letters are converted into its respective integers, into respective numbers. So for example, when I say A is equal to 0, B is 1, C is 2, D is 3, and so forth. So for example, these numbers are what is actually stored inside the memory. So when you're actually printing the characters, you go into the memory, you see what number it is, and you see what corresponding letter it is matching with. So whatever letter it is matching with, it prints that. The similar way, this is what is happening over here. So in 0x6f is inside the range of ASCII. So let's see what actually the ASCII range is. Okay, so this is the ASCII table. So in this particular table, you can see that from this, so from 32 to 126 or 127 is where all our basic letters lie. So for example, the capital letter A is having the value 65, the small letter A is having the value 97. So just keep that in mind. Once you start to solve more and more challenges, this will become a second nature. So you shouldn't really worry about that. So in Python, to convert a particular hexadecimal into a character, you can type chr and in brackets the particular value. Okay, so you get O. What is 68? H. What about 65? Get E. Okay, fine. So most of these looks like character. So all these are characters which is getting stored into the variable. Now let's see what these are stored for. So like I said before, you don't need to really care about these lines. You just need to care about these lines over here. So let's say, so local 3c, if the while loop will run until 0x27. So what is 0x27? 0x27, okay, 39. So it runs until the local 3c, the counter reaches 39. So it runs 39 times. And local 3c is used as an index or a counter. So if you know, if you know programming in general, you will know that array all the arrays are actually indexed using a particular counter, or a particular iterator, which is like a term. So you actually use those counter to actually get each of those characters or each of those bytes inside that array. That's what is happening here in general. So let's decode them in one line by line. So in this particular left hand side, you would see that local 37. So what is a local 37? Let's scroll up. Local 37. Okay. So local 37 are these characters over here. So each of those characters inside local 37. So it is getting okay, so each of those characters inside local 37 is accessed and it is XORed with the number 6. Now, this particular symbol you see over here is called XOR. So, XOR is like a bitwise operator, just like addition, subtraction, multiplication. there are several other stuff like bitwise and bitwise OR, and XOR is one of them. So this kind of does some kind of a mathematical binary operation on the binary digits itself, and eventually you will get this particular some kind of a result, and that result is stored back into local 37 local 3c. So that's the only thing what you can get from this particular statement. So if I'm repeating once again, all the characters are indexed inside local 37. It is getting XORed with the value 6. Now the funny thing about XOR is it is reversible completely. Just like addition has a reverse called subtraction. So like if you're doing 1 plus x is equal to 2, you can get x is equal to 2 minus 1. Simple. In XOR also, if 1 XOR 6 is equal to some particular value, and if you need to find what x is in that particular scenario, you can just XOR that value that is supposed to be as output XOR with that particular number. So it's basically just like A XOR B is equal to C. So if I need what x is over here, I just need to XOR this with A and I'll get x. Simple. If it was in case of addition, I'll need subtraction. If it was case in multiplication, I will need to divide. In case of XOR, I'll need to do XOR itself. So that's really interesting, right? So just keep that in mind. So we XOR two different numbers over here, one of them which comes from here and another one which comes from here, and that is stored back into local 37. This is outputted character by character, and this counter is getting incremented. So local 3c gets incremented one by one. Fine. So I think we got the whole gist of the loop. So once again, if I'm repeating, the loop runs for 39 times. Each character from local 37 is accessed. It is getting XORed with the number 6, and then in the second line it is getting outputted. The third line, the counter is increased, plus 1. That's it. Now this particular function is called when our input is same as to say something. Now let's try supplying to say something itself. Let's run the program once again. To say something, enter, and there we go, we get the flag. Now how did we get this flag? Remember I told you that we have this particular function over here called print flag. So all these characters over here, if you want to manually get the flag actually without giving the input, you can just copy all this. Yeah, you can just copy all this. You can paste it. Paste it over here. Give me a sec. So I just extracted all these bytes over here, and all these bytes are the same bytes what I got over here. So I just extracted those. Now you can give that into, I'll just store it into a variable called encrypted bytes. Alright. And we know that every byte of this is taken and it is XORed with 6, right? So key over here is 6. Now let's, how many times does the loop run? 0x27, which is 0x27 is 39. So for I in range of 0x27 or 39 in this case, I'm going to print every value of encrypted bytes XOR with the key. Okay, now this must be converted into character. So I do this, I wrap it around the function char. There we go. So we just do end is equals to 0 and it should give us the flag. Why does it not give us the flag? Alright, I had some slight issues, sorry for that. So once I copy paste that properly, and let's close just like before, and that should give us the flag. We got the flag without even running the binary or giving the right input. So this is how you can solve a particular challenge. So in this particular video, we learned how to use the tool called Gitra, how to read a decompiled code and understand how the function works and all those stuff. So I hope and good luck for you guys to solve more reversing challenges. Practice. So thank you for sticking with me and have a great day.